So what we are talking is that suppose this is what you have got, and diatomic molecule, as you know, has 2 rotational degrees of freedom. So each rotational degrees of freedom contributes r by 2 in the whole rotational contribution to the specific heat. Okay, that is obvious. Now given this, let us come to the next question, and that next question is like Fv. In the previous case it is Fj. And what is Fj? Fj is the fraction of molecules, fraction of these molecules in their jth rotational level. So fraction of molecules in the jth rotational level. Okay. Now even if this is the case, so what is this? This is, as you can easily realize, this is minus theta rotational j into j plus 1 divided by t. Okay, and this divided by q rotational t. So if we consider the previous assumptions, necessary assumptions are true, then this gives a very nice expression, 2j plus 1 into t by theta rotational, so theta rotational by t. Okay, you can say this has got q rotational is t by, so here is a sigma also in principle, and then you have e to the power minus theta rotational j into j plus 1 divided by t. So that is your Fj. Okay, now Fj is that the fraction. If this is the fraction, you can see now it has got an exponentially moving forward kind of, increasing term, rather decreasing term with respect to j, and this one is the increasing term. So if j seem to have a passing through a maximum kind of, and to find out at what value of j it is maximum, we find out that actually if you find out dfj, here also we are considering that practically this j is taken as almost a continuous variable, so differentiation must go to 0 at the maxima of fj, and if we substitute it, just differentiate it appropriately, put it 0, that means you differentiate this term as twice, and then suppose this term I say a, so this is suppose a, so we are saying this is a, and then e to the power minus theta rotational j into j plus 1 into j by t, and this is the differentiation of this, that gives 2, and then differentiation of this term will give minus whatever 2j plus 1 remains into a, into this term differentiation will give me minus, and then theta rotational 2j plus 1, what happens, 2, and then differentiation of this will give me 2j plus 1 whole square, is it? 2j plus 1 whole square, and then you have e to the power theta minus theta rotational by t j into j plus 1, because this term is exponential term, is not 0 at a finite temperature, so when you put it 0, then it becomes essentially twice a. A also is not 0, so you can take it out, so or 2 minus 2j plus 1 whole square, j minus plus 1 whole square, that equals to 0, is it? Or what happens is that okay, 2j plus 1, sorry, here minus theta rotational by t is there, theta rotational by t. So once you have that, you take it other side, and then you, is it theta rotational by t, differentiation, yes, so this is right, so it goes there, so it is 2t, is it? This j expression we want to find, so 2t by theta rotational, so let us just do it. So this we take it out, so 2j plus 1 whole square equals to twice t by theta rotational, or 2j plus 1 equals to 2t by theta rotational to the power half, or j equals to half 2t by theta rotational to the power half minus half, something like that, and that equals to, then it becomes t to the power 2, you can take out 2 theta rotational to the power half minus half, something like that, right? So j, that is the, or j is this. So this expression, which is the most probable rotational quantum number at which the population is maximum, or the fraction is maximum, or the probability of finding the particle is maximum, and the j in p is essentially t by 2 theta rotational to the power half minus half. So that is a nice answer. I think this has been referred in your spectroscopy class as well. Of course, here we have considered that j is a continuous variable. So once you have that, ultimately we have found out the rotational contribution to CV, as well as we also realize, unlike in the case of vibrational population of the particles in the vibrational levels, where the highest most populated state is the V equals to 0, that is the ground state. In this case, this is not the case, and in this case what happens is you have a maxima through which it passes. And you will see in my note also there is some data calculated for a given particular case of carbon monoxide at a given temperature, room temperature, and how it looks like, and we will see how the curve also looks like in a way. Now what remains is that finally for diatomic molecule, what we wanted is Q, rotational quantum number for a diatomic molecule at a given temperature and volume, and then that is equals to Qt into Q rotational into Q vibrational into Q electronic and then Q nuclear. So now most of the terms we have actually calculated. So Q translational is nothing but twice pi m1 plus m2 twice pi mkt by h square, so that to the power 3 by 2 into v. So that is the translational part, and the rotational part, just now we have seen that this is sigma theta rotational, that is the part, and the vibrational part is e to the power minus theta vibrational by 2t divided by 1 minus e to the power minus theta vibrational by t. And then the electronic part, actually we discussed very briefly, and that if we consider that the main contribution comes from the ground electronic state, that the molecule on a whole remains mostly on the ground state, otherwise there will be a second term here. So that for the time we are ignoring that second contribution, and the nuclear part, as we said, for singly degenerate states, that becomes 1. So ultimately that the molecular partition function for a diatomic molecule becomes like this, and once that is there, we can find out capital Q under the necessary approximation, that qvt to the power n factorial, and from here for the whole system we can find out E, that is kt square del ln q by del t, using this and other properties as well. And also we discussed about this AV and AJ, which shows certain interesting behavior. So here more or less we are stopping with regard to the discussion of macroscopic size containing huge number of molecules of the order of Avogadro number of molecules. Now the remaining part, we'll discuss something related with temperature. So that will be a separate discussion.